Hi, warm greetings. My name is Farhana and I'm from University Kebangsaan Malaysia. Today I'm going to talk to you on the current trends and challenges of additive manufacturing, multi-material and also 4D printing. So these are my team members and this project is collaborating with few industries such as Oryx Advanced Materials Neighborhood and also ORS Technology. So regarding 3D printing, or also known as additive manufacturing, is the current manufacturing trend in powder metallurgy. So these are the sequence on how to produce or print a 3D printing, starting from design using CAD 3D modeler, then you convert into STL file, then you undergo a slicing software to get the best or suitable printing parameters, and you print your design according to the shape that you want, and finally you get or you obtain the 3D object. So via 3D printing, we can produce complex geometries, intricate structures with internal cooling channels such as lattice structures, and it is quite applicable to polymers, metal, composite, and also ceramics. And it is widely has the potential to be applied in biomedical, automotive, aerospace, and others. And it is comparable to conventional powder metallurgy techniques such as joining, casting, and also powder injection molding. So in metal 3D printing, the common technique is known as laser powder bed fusion, or in short, it's called LPBF. So the common metals are stainless steel, titanium, and aluminum alloy. So you can see the schematic diagram on how it is conducted, and the main processing parameters are laser power, scan speed, hatching distance, and layer height. And the relation of these four main processing parameters resulted to volumetric energy density (VED). So due to repetition of printing process, which consists of melting and solidifying, residual stresses are easily formed and stored in the SP part. So distortion, warping, or maybe deform are possible to occur if the residual stress are not removed. So in order to reduce or remove such stresses, usually we use annealing heat treatment. So by joining two or more material in a component or an object is not something new, because we can easily achieve by using other joining techniques such as brazing, welding, and even powder injection molding. So these images shows our research team. We have conducted several pairing of different material in one part using powder injection molding, such as 17-4pH stainless steel with yttria stabilized zirconia, and also stainless steel 316L, and also 17-4pH. So printing two or more materials is possible with additive manufacturing. So recent trends shows increasing interest in MMAM. So this shows how you can conduct two different material in one part. So you can see that for material A, and then you slightly printed and you join by the second material, which is B, and it is printed layer by layer. So the interest of MMAM started in 2014 when NASA usually printed a single part consisting different metal alloys for aerospace application. So as you can see in the figure, you can see that the two materials are stainless steel 316L and copper chromium zirconium, which is suitable for high temperature applications such as heat exchanger and rocket nozzle. So how MMAM via LPBF can be feasible? So we need to select suitable material, which is metal, and processing parameter, and we also need to identify the printing strategies. So good printability depends on the thermal profile of the metal, such as thermal coefficient or maybe thermal expansion. So without good printability, unwanted issues such as residual stress, distortion can be reduced at the joining region, and we can produce a good printed part with promising behavior. So MMAM can be categorized in several functional graded materials, FGM, such as sudden change, gradual change, and ladder change. So in this project, we're gonna distinguish or even to evaluate the behavior of sudden change. So I mentioned just now that residual stress is commonly reported in LPBF due to repetition of melting and solidifying molten metal particle during printing process. So we can see that cracks are easily formed at the joining region due to the residual stress. So we can reduce that by using heat treatment. So we can see that the properties or maybe the performance improve after the heat treatment. So in this project, the materials that we use is stainless steel 316L and 630. Take note that 630 is also known as 17-4pH. So why we choose these two metals? Because it has a unique combination, which is 316L is austenitic and non-magnetic, while 630 is metasintic and magnetic. So the powder size ranges between 30 to 40 micron, and it is nearly spherical shape of powder particles, and it has thermal profile differences such as CTE, coefficient of thermal expansion of 16 and also 11. So it will be an interesting approach on the printability using LPBF, which is MMAM, since we have achieved a good result from powder injection molding. So these are the powder characteristics of both metal 316L and 17-4pH, or also known as 630. And the printing process consists of these processing values of laser power, layer height, scan speed, hatching distance, and BED. So you can see that these are the sequence of how the printing looks like. So next we have to identify the properties. So here is the printed sample for cubic sample. As you can see, it has a different distinct color between these two materials. And these are the tensile bar, printed tensile bar. The joining region is here so that you can see a different color or tone between two materials. And next, we can see that all samples seems to be intact, good bonding, so we can assume that good printability is achieved. But we need to perform based on other mechanical properties such as hardness and also tensile and also microstructure analysis. So due to possible of residual stresses, heat treatment was conducted at 800 and 1100. So we need to go for the next, which is mechanical and microstructure analysis. So this is the hardness test. So we can see that when we compare between 316L and 630, 630 has higher in hardness due to metasintic structure compared to 316L, which has austenitic structure. But however, it's quite interesting to know that the joining region here shows somehow a combination of the hardness value below, average, and also higher. So joining region has the combination of hardness for both metal. So hardness increases at the joining region due to 630 of the metasintic structure, and we need to validate through microstructure analysis. So based on the microstructure analysis, we can see that electroetching was conducted using oxalic acid at 7 volt for 80 seconds due to difficulty in normal chemical etching. So we can see that a good fusion of 316L and 630 at the joining region. We cannot see any delamination nor cracks were observed, so we can get possible intermetallic compound IMC. So twinning phase of 316L clearly fused together with metasintic phase, and we can see for the heat treated part, which is on the right side here, formation of melt pool is a bit hard to identify, and we can say that IMC may dissolve and possible formation of metastatic precipitation due to the higher hardness. So next is the tensile strength, and we can say that although the printed or the joining part was here, but the bonding region is really strong compared to the fractured section, which is it broke at 316L due to lower hardness. So the result for tensile is similar with hardness result phase, and the sample breaks at 316L, which indicates the weaker zone and clearly shows that the bonding region has a significant strength of bonding. So next, for the conclusion for the first part of this project, a good printability of MMAM using 316L and SS360 is achieved. Therefore, MMAM part having good performance is feasible. So we able to obtain promising performance on the hardness and tensile, and also the microstructure shows a good fusion of 316L and 630. However, hardness and tensile strength increase after heat treatment due to precipitation of SS630. So these are the references that I use for this project. So the next one is 4D printing. So this one is collaborated with industry as well. So why we need 4D printing? Because we know when we use metal in 3D printing, they tend to break or fail due to very high temperature and due to harsh environments such as extreme vibration or impact. So we need kind of like a sort of a special or maybe unique metal to undergo or maybe to overcome such issues, so that we need to have some elasticity properties. So we use shape memory alloy. In shape memory alloy, the common type is known as nickel titanium NiTi. So why NiTi? It has a superior shape memory behavior, and including high magnitudes of shape recovery, recovery stress, and superelastic strain. So it can be used in aerospace, biomedical implants, and actuators, and others. So, however, it is difficult to fabricate NiTi parts due to compositional sensitivity and poor machinability. So we can only produce simple geometries such as wires or even tubes, and we can also produce that by using machining or even welding. However, issues such contamination may occur during the fabrication process. So why we use different? Okay, since AM can use LPBF, so we would like to use shape memory alloy in this 4D printing. So we can easily relate to a NASA project, which is Mars rover, where they use NiTi nickel titanium wheels for their aerospace application. Next, for another part from Mars rover, we can use also fabrication of stent made of nickel titanium that is possible to treat blocked or maybe narrowed arteries such as in human hearts, and this is due to SMA stent are capable to be extended or even shrunk according to the size of arteries. So next. Okay, according like for my first example, so the concept is the same. The processing parameters and also the equation that is used to identify the volumetric energy density. So it is reported that excellent SMA behavior can be achieved when the laser power is less than 100 watt and scanning speed is between 1 to 5 millimeter per second. Next, by using the same equation, we can get linear energy density. That means we eliminate hatching and also layer height. So in this project, we're going to use linear energy density, not the volumetric energy density. So we only change the value of laser power and velocity. So the value of P over V is between 0.1 to 0.3, so that the tendency of formation of large pore is controlled, so that it won't be too high. So we need to control that. So next. So by using SMA, so another properties that it is interesting to be probed is the cyclic tensile stress, which involve heating the product made by nickel titanium at high temperature. So cyclic tensile test can be referred to as a fatigue test due to the involvement of loading and unloading cycles until the part fails, which is under the harsh environment. So we can get several shape memory effect behavior such as ultimate tensile strength, total recovery strain, and others. So each tensile sample will be subjected to 10 cycles. So for each cycle, the samples will be loaded at 400 megapascal and unloaded at 10 megapascal. So after 10 seconds, the tensile bar will be heated to a temperature austenite finish plus 30 degrees Celsius value at the rate of 5 degrees per minute. So we can get the recoverable strain after heating and recovery ratio and others. So these are the references for this project. So please take note that this project is on the initial stage where we are still doing the printing process using the nickel titanium, and we assume and we highly believe that we can get a good properties by using this kind of parameters of linear energy density, where we change only the value of laser power and also velocity. So that's all from me, and thank you everyone for listening. And I would like to promote our own journal, Journal Kejuruteraan, or in English is Journal of Engineering, by our university, University Kebangsaan Malaysia, and we are indexed in Web of Science as key. And we have our own very own impact factor 0.6, and these are my emails, and I hope to receive or maybe to get a feedback from you guys, and also to receive submission for our journal kejuruteraan from you guys. Thank you everyone, and have a good day.